delta t. This is this comes from the fundamental concept of calculus, right? You do this, and which is equal to y of 1 minus y of t. The RHS remains the same, 1 minus y of t, just the LHS changes, right? The place where you have the derivative, that changes into y of. So this is simple forward Euler. And once you rearrange the terms, you get something like this: y of t plus delta t equals y of t plus delta t 1 minus y of t. Now here what you have to see is this: the value of y at a future time depends on the value of y at a past time, right? One time step before, and so on. So you know that y of 0 is 0. So if you start from this point, so you know that y of delta t will be y of 0 plus delta t into 1 minus y of 0, correct? And so on. Now you get y of 1, and you can use y of 1 to calculate y of 2, y of 2 to calculate y of 3, and so on, right? This is how you generally solve a forward Euler problem numerically. And when you have when you do this thing in first, you calculate time t equals 0, then time t equal to 1, time t equal to 2. When you march on in time, it's called marching on in time, MOT. That this process called time marching method, correct? So I'll just give a simple graph. So the purple one is the analytical and the dotted one is the numerical value. And this is for a given discretization. If you reduce the discretizations, make the discretization smaller and smaller, you'll get a more accurate matching between the analytical and the numerical solution. For example, I'll just run this code. So this is the analytical solution. Here I have just plotted y equals 1 minus e to the power minus t, which is the analytical solution. And numerically I have solved. That is, if ii equals 1, that is when that's the first time, you know the solution, it's y of 0 equals 0. For all the other times, you know y of at that time equals the previous y plus 1 minus previous y into delta t. This directly comes from this formula. You're able to see the MATLAB screen, right?
Yes, yes.
Yeah. So this is very straightforward, right? And at every time you use the previous y to calculate the new y. So if I run this, for example, this is at 0.3, delta t is 0.3. You can set delta t to whatever value you want, but only the difference is as delta t changes, increases, your accuracy will go down. For example, I run this. As at every time you get a new y, and so this is how you numerically solve a simple differential equation, first order differential equation. And if I reduce the delta t to, let's say, 0.1, you're also able to see the graphs, right? The plots.
Yes, yes.
Yeah. So see, as you reduce the delta t, the matching becomes closer and closer, but it takes a longer time to settle down, longer time to get a solution. Correct. Now this was a simple first order ODE. Maybe you'd be thinking, I mean, why am I going through something as basic and as simple as this? But the point is this: you can actually explain a lot of complex processes by building on some simple such numerical routines, and you'll be fascinated by the results that you get. So this is a simple equation. Let's say you have we'll take it a notch higher, right? So let's say a coupled equation, that is, you have one dou q dou t depends on dou p dou z. That is, you have two variables. There's a q that varies with time that depends on a p that varies with z. And this is just a proportionality constant called b1. But you have to concentrate on b1. It will be useful in future times. You'll notice. So this is one equation. And second, the dual of that is dou p dou t equals b2 dou q dou z, right? So these are two coupled equations. And you have to solve this differential equation. Now, in the previous case, you wanted to find y at all the times, right? This is what you did. You wanted to find the value of y at all the times. And you were given the value of y at one specific time, that is t equals 0. In this case, you are given one of the two quantities, that is, you are given q at one particular z for all times. That is, it could be a source, for example, a voltage source or any kind of source, right? That's how it works. That is, you put a voltage at some point. So you have the q at z naught for all times. It is given as this kind of equation, e to the power minus a squared t minus t naught whole squared. This is a very common way to represent a source. This is a Gaussian source. And one reason why we usually use a Gaussian source is because it is continuous, it is infinitely differentiable, and most importantly, when you see a Gaussian source, if you take a Fourier transform of a Gaussian source, right, again you'll get a Gaussian source. That is, the Fourier transform for Gaussian is a Gaussian, right? If you take it, you will see. So that makes it very simple to convert a solution from a time to frequency and frequency to time domains. But that's for some other day. So let's say this is the initial condition in this case. That is Z not. In this case, we don't call it initial condition, we call it boundary conditions, or some condition that is wherein you are given the value of Q at a certain point for all times. And now your goal here is to find the value of Q at all the Z values at all the times. And similarly, you want to find the value of P at all the Z values and at all the times. Right? Now, how do you do that? You do the same thing. You first discretize the first equation. When you do that, or I'll start with the second equation. You'll discretize the second equation. When you do that, it's very simple. P, it's d dou p dou t. So you have to find the first order differential with respect to time. So pz t plus delta t minus pz t by delta t. That is, z is constant. This is a partial differential, right? So z is constant, and you find a derivative with respect to time. That's what partial differential means. So you have to keep one variable constant and find the change of that parameter with respect to the other variable. So p, so this one becomes equal to b2q z plus delta z comma t minus qz comma t by delta z. This is very straightforward. Similarly, you do for the first equation. So you got two equations here. Now, what you do is you try to rearrange the terms. That is, you find the value of the future time in terms of the previous time quantities. So here, t plus delta t is the future time, and t, and t, these are the known values. You would already know from the previous time iteration, right? That's how in the previous case you used y0 to calculate y1, y1 to calculate y2, and so on. Herein, you use pz of t, that is the previous value of p at the previous value of time, and q at the previous times, and q at the previous time to calculate the p at the current time. Right? So that's how you rearrange. So these are called the update equation because you are updating the values, right? So this is the first equation. So this is how it forms. So pz t plus delta t equals pz t, plus. So this is how it comes. And when you do that for the second equation, what you get is this. Similarly, for t plus delta t time, to evaluate the q, you need q at the previous time plus p at the current time. You see here the indices are the same. T plus delta t, t plus delta t, and t plus delta t. You get these values from the previous equation. See here you calculate p z comma t plus delta t. That is, so this is how you use the solution of the first equation and plug it into the second equation. So you get qz t plus delta t, and then you use the second equation again, plug it into the first equation, and it just keeps going. So I'll just show an example of how you do this on MATLAB. So I just assume two values, b1 and b2, and these are very important that these are negative to get a particular form of result. If you set this as positive, you'll get a different kind of result. Right? So these are b1 and b2. These are the proportionality constants in the previous equation. And then again, you assume a spatial discretization, something, and you assume a temporal discretization. Now, in this case, you see that the spatial and the temporal discretization are related by a, you give one value of spatial discretization, and you don't just delta t, you just don't give any arbitrary value. It depends on delta z and another parameter v, and this v is given by square root of b1 comma square root of b1 into b2. So this is very important to notice that the v, we'll know, we'll later find out what v is. V is actually the velocity of propagation, correct? So, and it depends, and
This is
these
a
are
wave
very,
equation.
yeah, I was coming to that. I wanted to show the wave first, so then come to the wave. So basically, here the delta z, the spatial and the temporal discretizations, they should be related to one another. And for the optimal solution, they are related to each other by the velocity of wave, that is v. And the v here is square root of b1 into b2. This is the proportionality constant, b1 into b2, and the square root of that will be the velocity of the wave. Correct? And now we do this usual temporal time marching routine. That is, you start from t equal to 1 to nt minus 1 or nt, whatever you want. And the z should be 2 to nz minus 1. Nz is the number of spatial steps, right? That is the because you want to find the solution at some z values. So that span of z is given by nz, your number of spatial points. And similarly, number of temporal points, at how many time values you want to find the solutions, that is nt, right? And I used nt and nz as some multiples of delta z and delta t. So it's very simple. Now, first thing is source. The source in this case is the initial condition. Q of z naught comma t is given by this. So this is what I did. I assume the source at some point, which is at the center of the whole span, right? So Q at nz by 2. Let's say you have 10 points. I assume that the Q at the fifth point is this Gaussian source, right? This is the given. So we call it source, or you call it some kind of a boundary condition or initial conditions or something, right? So, and now we go with the update equations. So update equations is very simple. Pz. So now here the indices 2 and 1 are, 2 is the current time step, and 1 is the previous time step, that is y0, y1, y2, y3, right? So I just use two of them, the current one and the previous one. You don't have to store all of them. You just need the current. You just want to find the current value from one previous value, because in this case the current value just depends on one previous value, not all the previous values. If there were an integral, it would depend on all the previous values, but here it just depends on one previous value. So pz comma 2 is given by pz comma 1 plus b2 into, I just use the previous expression, this form. And now you get pz comma 2. Now it's not a z comma 2. You find the value of, since the z loop is within the time loop, for any time you are able to find the value of p at all the spatial points, right? So you know p at all the spatial points at the current time, at the latest time. Right? Now you use this value pz comma 2 in the next equation for q. You find qz comma 2 by using qz comma, the previous values you already know from the previous equations, and like this. So after, for all the z you do, then for all the times you do. So this is how you update the equations for a coupled equation. It's very straightforward. It's very similar to the if you understood if you understood this equation, it's very similar. You have to follow the same procedure for a coupled equation, but the results that you find, right, they are really beautiful. Yeah, so the results that you find are really beautiful. For example, if I run this case, so I put a source somewhere in the middle for Q. So, and the Q was a Gaussian, right? Now you can stop the simulation at any point. I have stopped the simulation at this point. So you had the source at this point, correct? And it was a Gaussian source. That is, it was time bounded. That is, between certain point and certain point in time, it appeared. But as it vanished from this point, you see that the source was moving on either directions. That is, initially, these are z values. Initially, at this point, you did not have any p or any, and at this point, you did not have any q. But as time progresses, you see the wave is moving on either directions in the z-axis, right? So this is called a wave. So see, the wave is moving in z. And now, okay, now here another question is there. You took a span of L as, in this case, 6.06 meters. Now what happens after that point? Should the wave keep going? For example, when you have a wave in a swimming pool, it hits the boundary wall and it reflects. But here we have not actually defined what the boundary is. You know there's a boundary at 0 and you know there's a boundary at 0.06, but you have not told what kind of boundary is. Is that a boundary that would just allow the wave to keep propagating, and you have just, that is, if you have an infinite space, you cannot model the whole space. You have to truncate at some point. But if a wave is propagating, just see an infinite space and it will just keep going, right? So that can be one kind of a boundary, wherein the boundary should behave as if it were an infinite space. Or the second kind of boundary is if you have some kind of a wall, the wave would hit the wall and come back, correct? So that would be another kind of a wave, another kind of a boundary. So in this case, we have actually not defined the boundary in any manner. We have just updated the equations and you see the wave going. At that boundary, it becomes kind of undefined because you are not told what kind of boundary it is. So it just behaves arbitrarily. So the solution is valid from 0 to 0.06, but beyond, at those two boundary points, it's not valid. And after it returns from the boundary, again, it's not valid for those times because you have not actually told what kind of boundary it is. Correct. So this is one thing. And another thing that I would want to show is this. Which time do I have? Oh, okay. So another thing, let's say you have delta z and delta t are governed by a certain relation, right? So delta t cannot be any different from this. If it's different from this, you will get results that are not optimal. Let's say you make it twice, you make delta t twice of what it was previously. And when you run it, see, it becomes very arbitrary. This is called, it kind of becomes very unstable. It just keeps going. This is not the kind of solution that you want, right? So that's why you have the spatial and temporal discretization in these cases, these kind of domain-based methods, time domain-based methods, they are related by a certain value. If you make it, let's say, smaller, 0.5, so here you will get a different kind of problem. See, it becomes very slow, right? So it's not actually behaving the way the wave should propagate. And another problem you'll see in some cases, acute cases, you'll see something called dispersion. What it means is that the different frequency components would uh, go at different velocities. So that's another problem that you would face in such cases. See, for example, here in this case, you see a small king. So this should not happen usually in these cases. Here also you'll see this thing. It means that the wave is dispersing. That is different because it's a Gaussian, right? Gaussian will have a lot of frequencies and each frequency should travel at the same velocity. But if you don't follow this kind of discretization condition, it's called CFL, Courant Friedrich Levi limit. It's called CFL condition. If you don't follow these conditions, it will cause these kind of dispersions which are artificial. So another thing here is this, you can actually derive this. Eventually, these are what are differential equations, right? So you can write it in the form of matrix, wherein x of n plus 1 equals a x of n. That is, A is a system matrix. And for a system to be stable, the eigenvalue, if it's a continuous time system, the system matrix should have eigenvalues, which are all, which the ones, the eigenvalues of the system matrix should always lie on the left-hand side of the S plane, right? And for a difference equation, the eigenvalue should lie within the unit circle. Now, if you do a careful analysis, you will notice that if you increase the value of delta t more than this, you will see that the eigenvalues will go out of the unit circle. So it will become unstable. So that's one way to see why you don't get a very good solution if you change the value of delta t. Right? So this is one example that I wanted to show. And another thing is, okay, let's say if I make it, the thing is, the wave propagates, right? That is at certain point of time. That is at any point of time, the wave at some point of time wave is here, then it moves and so on. So the wave velocity, if you calculate, right, it will exactly be equal to this v. That's square root of b1 comma b2. That is, if it goes from 0.03 meter to 0.06 meter in certain time, if you divide that delta 0.03 by that delta t, you will exactly get that v. This is the wave velocity. Correct? So this is something that I wanted to show. Okay, and this was just a simple case wherein we did not get into any kind of electromagnetics. This could be any kind of wave, just P and Q. You don't know what kind of, this could be a water wave, or this could even be a sound wave. You don't even know that, right? So, but we have not actually said that this is an electromagnetic wave, right? But if it were an electromagnetic wave, how would we arrive at this kind of an equation? This is a very simple equation, right? You'd probably think that there's no electromagnetic wave that would look like this under no scenario, because you generally have electromagnetic equations that look like this. This is one electromagnetic equation. This is the curl equation, del cross E equals minus mu dou H by dou T, right? This one equation. And when you expand this whole thing, it becomes something as complicated as this, right? And the second curl equation that you have for in Maxwell's equation is this. Herein, we have not even considered the displacement in one of the cases, right? So in the second equation, the curl equation del cross S, H equals epsilon dou E by dou T. And again, if you expand it, it will become something as complicated as this. Now, for let's say you're modeling an antenna or a radar system, then you will have to go for all these kind of crazy. You'll have to consider all these crazy differential when you form the difference equation. That is, you have to discuss each one of them and separate the variables and march individually in x direction, y direction, z direction, and then t. You have to march in all four of them. But for the sake of this presentation, we'll just take a simple. If you want to model antenna, you'll have to take all of them, right? And you probably won't even use them in this form. You will use in cylindrical coordinates depending on what kind of antenna you're using. So it can become complicated in a different way. But assume that we only take a very specific case. That is, let's say this one, a plane wave case. That is, the wave propagates only in the z direction. Okay, that's one thing. And only Ex and Hy are non-zero, right? So when you put all those conditions in this, only Ex and Hy are non-zero, and Ex and Hy do not vary in X or Y. So that is, you have the differentials of E with respect to X or Y, they are all zero, right? In this case, you are left with only two equations, that is -1 by mu dou Ex by dou Z equals dou Hy by dou T, and the second equation. These are only two equations that you are left with. And see, this is uncannily similar.
Right?
Pardon?
You're talking about a polarized wave. You pass a
Yeah,
normal wave or a
correct.
stream of light through a polarizer, and then you just get
Yes.
waves in one plane.
Yeah. Yeah, you just get a wave in one plane. That is, E only has a component in the x direction, H only has a component in y direction, and the wave only propagates in z. That is, you have the variable dz. That is, the wave only changes its value in the z direction. It only propagates in the z direction. And it's very similar to the previous equation that we saw, except that you had the p and the q here, q and the p here, and the constants were a and b. So to solve this problem, you use the same kind of procedure. You differentiate each one of them with x and this one with y, and similarly this one with t, the RHS with t and the LHS with respect to z, right? When you do something like that, use the same kind of procedure. I use the superscripts half and minus half. It's just for the sake of ease, because it's easier for, it's called leapfrog algorithm. That is, okay, I won't go into that. That's a bit complicated, but you can use the same procedure that I told, that I described in the previous example. And when you do that, you get these two update equations, right? These are very similar to the update equations that you saw previously. That is, you find the H at k plus 1 by 2, and sorry, H at n plus 1 by n are the time variables, k are the space variables. So H at n plus 1 by 2, that depends on H of n minus 1 by 2 and the previous values of E. And similarly, you use these H to find, see, you have H n plus 1 by 2 here. And these values you evaluate from the previous step. And you evaluate Ex n plus 1. And so on. And for the next time iteration, these would be the input. And you evaluate Hy and then you evaluate Hx. So this is called time marching scheme, right?
So if you can just show the maybe a small diagram that H will be at the center points and E will be at the edges, right? In this kind of an equation.
Yeah.
Do you have
But
that diagram by any chance?
I don't have that. I thought that was a bit complicated to understand. I just didn't go through that. But I just wanted to explain how to solve this problem. It's called a leapfrog mechanism. So that you can go through and check it out. It's called leapfrog method, and that's the way the wave propagates in space. But that's more intuitive, so it's difficult to explain it here.
Yeah,
So,
I mean,
but
like discretization takes.
yeah,
It's
correct.
basically a kind of discretization
Hmm.
perpendicular to each other. H and E are perpendicular to each other.
Yeah. So I'll just show an example here. Same thing here. Let's say you have C is 3e to the power 8. This is very straightforward. How you get that is root b1 into b2, and that root b1 into b2 here is, so it's very beautiful here. So here 1 minus 1 by mu and minus 1 by epsilon, and root 1 by root mu epsilon, you know that that's 3e to the power 8, 3 into 10 to the power 8. That's 1 by square root of mu epsilon, which is the velocity of wave in velocity of electromagnetic wave in free space, right? So I directly use C 3 into 10 to the power 8, And here epsilon is 8.85 into 10 to the minus 12, and mu is 1 by root c square epsilon. So these are direct quantities that you these are physical constant. And again, in this case, I assume the length, the span of the space to be 0.06 meters, and delta z is 10 into 10 to the power minus 4 meters, and delta tc, again the space temporal discretization depends on the spatial discretization divided by the velocity of propagation c, right? And again, let's go to the simulation. Again, you have the time marching, that is the time marching from 1 to nt minus 1. So you first calculate the value of the field quantities at time t equals 1, t equals 2, t equals 3, and so on. And again, the inner loop is the z loop. That is, you have discretized the space in one dimension, and you are evaluating the value of ex and hy at each one of those z points, right? And the ex and hy will be perpendicular to one another. So it's very similar. So the first equation is this hz, and here again, the index 2 is the temporal index, which is the current time step, and 1 is the temporal index at the previous time step, correct? And z is the spatial index. ZZ is a spatial index. So you have HYZZ plus 1 depends on HYZZ plus 1 and the H at previous time step, and EXZZ plus 1 at previous time step and previous time step, so on. And this is the first space equation. And then the next update equation is in terms of E, because you have HY and then the HY leads to EX. So this is what you call, right? E. This is how the wave propagates in space. The H causes E, and the E again causes H again causes E. So it just keeps curling and keeps going around in space. So one has to cause the other. So that's what it means. H. So you have E that creates H that creates E. So again, EX at ZZ, 2, this is the current time step. It depends on EX at ZZ, 1, and HY at ZZ, 2, because you already know the current time value from the previous step, right? So these are the two update equations. And now I'll just run this case and then tell you about the boundaries, how the boundaries come here. So this one case, here you see the wave propagates and it just goes and doesn't come back. What it means is that you're able to model the space as an infinite media. That is, the wave goes and it doesn't hit the boundary wall and come back. It just assumes that the boundary wall goes till infinity and it just keeps going. But in this case, you don't have to discretize the space itself into infinite segments. You can just discretize it to as much as you want, and then you put some boundary conditions. And those boundary conditions would tell the wave that it's like an infinite boundary. One example that you find in circuit theory is this. I don't know if you're familiar with the transmission line theory yet. Some of you are undergraduates, I don't know. So if you have a transmission line that's infinitely long and you want to model it, you don't model an infinitely long transmission line. At some point, you just terminate it with a surge impedance, right? So in that case, the wave goes and doesn't reflect it. For a wave, for a source, it's as if the transmission line is infinitely long. That's what it means, correct? So you could just interrupt me if you are not familiar with this concept. So this is what one kind of boundary condition is. So you have different boundary conditions. For example, this boundary condition is called Moore boundary conditions, MUR. So this is something that you can go through literature and study. This just to introduce you to these concepts. That is, you are able to plug in specific conditions on the boundary wherein in such a way that the boundary will behave like an infinite space, correct? It won't reflect anything. So this is what I did. So here, if I do EC equals 3, this is a flag that I have used. If I set EC equal to 3, it directly applies the Moore boundary conditions, right? That wherein the space behaves like, where the boundary behaves like it's going through all through infinity. Now let's say I do something like this. EC equals 1. So EC equals 1 is a PMC. Herein, this is very similar to an open circuit. That is, you have an electric field. You just notice the electric field and the magnetic field, okay? Okay, at this point, you see the electric field is increasing. Okay, so I'll just come back again. I'll just run it again. You see magnetic field, it will reverse at the boundary. See, the magnetic field reverses at the boundary. And if you see the electric field here, the top window, you will see that as it goes to the boundary, it will double itself. You see, when it goes to the boundary, it will double itself just at the boundary point. It's at 1, it will become 2. Right? So this phenomena is very similar to what you see in a transmission line, which is open circuit, right? The voltage goes to the open circuit point and doubles, and it comes back, right? So that's just at the boundary, it will double and come back. And at an open circuit, the total current is 0, open circuit point. So the current wave that goes to the open circuit point, it has to reverse itself. So that's why the reversal occurs. You see, at it goes to the open circuit boundary point, the current has to reverse. Right? So this is what happens. So this is a way of telling the source that there is an open circuit at the other end. So this is one EC equals 1. And if I say EC equals 2, this is another boundary condition. This is a PEC boundary condition, perfect electric conductor boundary condition, which is like a short circuit. What happens in a short circuit? The voltage goes to 0. That is, the electric field should reverse now, and the current doubles at the open circuit point, right? At every time a current pulse goes, it doubles and it comes back. It doubles and comes back. Correct? That's how it happens. So if I set EC equals 2, it will be a PEC boundary conditions. And I have set the conditions for PEC here. That is EX equals 0. And the moment you set EX equals 0, right, it will automatically make the H value, which is equivalent to current in some cases, right, to double. So for example, I'll just run it. So you see the E will reverse here and H will double. You carefully see the second graph. The H will double itself. You see, it tries to double itself. And the E has reversed. It was positive, and then as it reaches the boundary, it becomes reverse and then comes back. So this is how you set boundary conditions in these cases for domain-based methods. So you have to know what kind of boundary it is. Correct? So I'll just stop this point here. I'll just give a small brief example here. I don't know if many of you are familiar with the transmission line theory, but I'll just give a simple example of what happens. Are you able to see as TL1.CIR? No?
Yes. Yes.
Yeah. So let's say you have a pulse. It's called it's a V1, and it's between nodes 1 and 0, and it's a pulse. It goes from 0 to 1, and it has a width of 5 microseconds. So it's a simple pulse. And you connect a transmission line between the nodes 1 and node 2, and the transmission line has a surge impedance of 50 and the length. So the length of a transmission line is given in terms of the time it takes for a wave to go through, because you know, right, the velocity of propagation and the time are proportional to one another, right? So the length is just velocity of propagation divided by the TD. It's called a delay time. And you terminate the transmission line by a resistance of, it's a very huge one, let's say 1 gigaohm, and you run the simulation. Okay, I ran the simulation and I plot at traces, and if I want to plot the voltage at node 1, I plot the voltage at node 1. It's 1 volt. This is the voltage at node 1. And if I plot the voltage at the node 2, which is terminated by a nearly open circuit, you see it becomes double the value, right? That's what happens at the open circuit. The voltage would double, correct? So this is exactly the phenomena that I showed you here. But except that in this case, it's voltages, and there it was electric field. And I'll describe how those two correlate, the electric field and voltage, similarly magnetic field and current, right? So this is the second case. This is the first case. And now let's say you you run it for a much larger time. Then you will see how it 120 microseconds, right? When you run it for larger time, you will see how the pulse looks like. So the source voltage will be like this. That is the source voltage. Okay. And at traces, it's a periodic wave, right? Because it repeats at 100 microseconds. So I'll just change it. I'll just leave it to a single pulse. I'll just make it 1000 microseconds and run it at traces V1. So you have the source voltage, a single pulse, and now you see the load voltage, how it changes at traces V2. Now you see the load voltage at V2 So you have a voltage V1 that goes to the load, it doubles, correct? And now the doubled voltage comes back to the source, but the source is shorted, right? Because there is no resistance at the source. You just have the source voltage and it's just a short. So at the source, it becomes reverse and it comes back to the load side, correct? And it doubles. Then again it keeps going. So this is how the so the V2, it'll just keep appearing periodically. So this is what is called reflection at an open circuit or a short circuit. I have one more example. Before that, I'll give a simple example, right? Let's say you have a transmission line which is broken at some point in the middle. It's broken at some point in the center. You don't know at what point it's broken. It's not center. It's at some point it's broken. So you apply voltage at the source, and when you measure the load, you don't get any voltage because it's broken. But you want to know at what point it's broken, right? So you give a source, and in the middle, there's an open circuit. So the wave will reflect at the open circuit point and come back. Now you measure the time it takes for the wave to come back. For example, you measure the time between the subsequent reflections, and then you will know at exactly what point in the transmission line you have a breakage. So this is how you see. It's called time domain reflectometry. So you can measure the time delay between the source, the voltage source that goes and comes back, and use that delay to find exactly where you have a fault or something. Correct? So this is something that's commonly used in industry. This reflection phenomena is commonly used in industry, and this is a simple circuit model. You can also do it. This is a simple spice circuit model. I'll send these files if you want, and you can practice. You can use multiple. For example, if you have a T2 that goes from 2 to 3, and it has a different surge impedance, Z0 of let's say 100 ohms, and TD of same 20 microsecond, and 3 0 at something. Now you'll see that you have multiple reflections. So you have a pulse that goes from 1 to 2, and at point 2 it sees a different surge impedance of 100 ohms, not 50 ohms. So it will reflect from there also, right? So you have multiple reflections in this case at traces V1, V2, and V3. So you see these kind of multiple reflections occur when there's a mismatch between the impedances of the transmission line, surge impedances of a transmission line. So this is what happens. And another thing that I just wanted to show you is this. It will be useful in the next simulation. That is, when you have a load that is larger than the surge impedance, right? In such case, the voltage always increases at the load side. Let's say you have the voltage at V1 and V2. So the V2 will always be greater than V1 if the load impedance is greater than the source impedance. So this is what happens. And let's say if it's smaller than the surge impedance, let's say 25 ohms at traces, the V2 will be lower than V1. And it will just keep getting lower and lower and lower, right? So this is what is going to happen. So it's a basic reflection phenomena that happens on a transmission line as the wave propagates. So this will be useful to you when you study about the propagation of over voltages in a transmission line. That is when a disconnector switch opens, you have very transient over voltages that go through transmission lines, right? That propagate through transmission lines. And those are very high frequency pulses. And then when they hit let's say a load like a transformer, you will have the magnification of voltages will be so high that it would damage the insulation between the sometimes even the bushings or between the turns and so on, right? So this is something that this kind of studies, you need to have a very good grasp of these concepts, how the wave reflects at the load or at boundaries between two different surge impedances to be able to understand how waves propagate on a transmission line and so on in real scenario. Okay. I have about 8 minutes, so I think I have one more example to give. So in the previous case, we spoke in terms of H and E. So let's say you have a simple transmission line and you divide it's one of the methods to model transmission line is a distributed circuit transmission line, right? LC, it's a ladder network, LC ladder network. So you have a source at this point and then you have some kind of a load at the other point. It could be a load, it could be another source, or it could be anything. Or you could have a transmission line or so on. right? And when you do a simple Kirchhoff's, I call it Kirchhoff, some people call it Kirchhoff, but I think Kirchhoff is the correct way to say it. When you use the Kirchhoff's law at each one of those sections, what you have is this kind of an equation. You eventually derive this kind of an equation: dou v dou z equals L dou I dou t, and dou I dou z equals C dou u dou t. Now you think that we made, so this is what happens, right? You had such a complicated equation, Maxwell's equation, and you simplified it to get something as simple as this. And you probably think we made so many changes and we got something as simple, and this probably is never used anywhere, right? But this actually has a very prominent importance. Prominent importance is I don't even, it's redundant, but it's so prominent in transmission line theory that you could nearly model all faults, VFTOs, or even in some cases the lightning phenomena propagating to transmission line using just these simple equations like dou v dou z, L dou I dou t, and minus dou I dou z, C dou u dou t. And L and C are the proportionality constants here, correct? And I'll just show you how to model this on MATLAB. So this will be the last example here. And so as I said, first thing you have to do when you are modeling a transmission line is to model the geometry. So I'll just show the geometry, how the geometry looks like. So this is geometry. You have one conductor that goes like this, and this is the transmission line, and this is the load point. And this vertical conductor is where I put the source, and this conductor is where I put the load. So this is how the transmission line looks like. And to model transmission line, you just use a MATLAB structures. If you are using C++, you could use a MATLAB class wherein segments would be the class object and so on, right? So you try to get as much information about a transmission line and store it in the structure this way. Okay, and now you see these equations are very similar to previous equations. So you can use the same FDTD method. Those are called FDTD method, right? Time domain marching methods to solve these equations. And so you have to first evaluate. So here the proportionality constants are the inductances and the capacitances, right? Capacitances and inductances of the transmission line. So you evaluate the capacitances and the inductances, and what you use is the potential coefficient methods. Okay, these are very simple numerical methods which you can find in literature on how to evaluate the capacitances and inductance between thin wires. That is, transmission line is just wires, right? To be able to evaluate the inductances and the capacitance between those simple wires, you can use the potential coefficient method and the Neumann method, right? And once you do that, I'll just run this case. I have like 5 minutes. I'll just simply run this case and I'll show you what happens. So similar to previous case, at the source location, you had a pulse, and the pulse keeps propagating, and at the load, it reflects and it comes back, and at the source again it doubles and again it goes, and so on. So what can you tell about the transmission line from this? See, this is the current and it reflects at the load, which means that the transmission line is open circuited, and it doubles, the current doubles at the source side, which means that on the source you don't have any impedance. So which is the condition that I have added here, that is the resistance at ns minus 1, the load side is very high, 1 mega ohm, and the source impedance is very low, right? If let's say I make it the reverse, at the load side I make a very small impedance, 1 e minus 5, and in such a case you will see that the current at the load will double instead of reversing. And I'll just run the case here. See, so you have the current, right? The current is propagating, and it goes at 1 is the load point, and it doubles at the load because I have short circuited the load, and again comes back, and the source, it again doubles and it goes back to the load, and again it will double, and so on. This will keep happening. Now a third case is this. I do something called a surge impedance loading. That is, I equate the load impedance equals to 330 ohms. In this case, I have kept this calculated the value of this characteristic impedance of the line as 330 ohms. And when I run this case, you will see there will be very little reflection from the load. It's not possible to match exactly, right? In these are numerical cases, there will always be some small So you have the current propagating towards the load. At when it reaches 1, you'll see a very small portion of this will reflect, right? A very small portion, which means that you have almost matched the load, right? And source is not matched, but the load I have matched. So this is another way of see again, and the amount of friction keeps going, keeps getting smaller and smaller because I have managed to match the load very well, right? So this is one real electrical engineering example wherein you can use the uh, electromagnetic phenomena and approximate it, and that would be directly applicable for an electrical engineering case for a transmission line, as I showed you in the circuit file with the SPICE example and in this simple MATLAB. And the iteration methods are exactly the same. That is, the current time voltages depend on the previous time voltages and the previous time currents. Similarly, the currents at the current time, they depend on the current at the previous time and the voltages at the previous time. So this is the update equations, correct? And so this, I think, finishes the examples that I had tried to show today. And it's almost 8, so I should wrap up now, I think. So some of the challenges that you face when you model conducting geometries or dielectric geometries using electromagnetic uh, computational electromagnetics is this. I have showed very simple geometries, a capacitor or a transmission line. But when you model an IC or an aircraft, it's a very complicated geometry. You cannot just use simple 1D equation and expect to get an exact answer. So you have to do a 3D simulation, right? Or in an IC, you have to take care of all the complicated chips, the pins, and even a small wire that protrudes from the PCB has to be accounted for such high frequencies. Let's say if you are working at 3 gigahertz, you have to account for every small conductor, even a small wire that protrudes from a PCB. Otherwise, it would cause compatibility issues, right? So that's one problem. That is, you don't have always a simple capacitor or a transmission line to model. So this is the first challenge. And the second challenge is I used a uniform design. That is, I divided the capacitor into equal patches or the transmission line into equal segments. But this is not always valid. Let's say you have a geometry wherein it's a sharp bend. When you have a sharp bend, you need finer discretizations there because the field magnifies there at sharp points. So you need height. So cannot always have liberty of uniform discretization. So this is another challenge. And you have to know where to discretize in what quantity. And third is singularity issues. That is, in the source and the load points are the same. So the denominator, that is, you have something, okay. Yeah, here. So you have something like this, Rij. So when I and j are the same here, this goes to a very small value. And in such cases, you can have something called singularity. That is, your matrix becomes inconditional, right? Ill-conditioned. And in those scenarios, you will have some singularity issues and you should know how to solve them. So that's another problem challenge that you might face. And the last one is this. The real world scenarios involve non-homogeneous media. That is, you always do not have mu naught and epsilon. It's not always vacuum, or it's not always air, or it's not always one dielectric. You have multiple medias. So in the case of multiple medias, you should be able to model each individual media differently. So that changes the discretization, that changes the way you model those individual medias and so on. For example, I used 2 transmission lines in series, and you saw that reflections occur from each one of them individually. So imagine you have multiple media. Let's say you are using a radar to detect a landmine or EM pulse to detect oil under the earth. You have so many medias on earth, right? Water and moisture, and it varies with every depth. And in such cases, you need much better modeling techniques. So these are some of the challenges if you are planning to take up EM as computational electromagnetics as a serious career choice. These are some of the problems that you would face and you should be willing to solve. So I think this concludes my today's presentation. I know I was a bit fast today, but I wanted to cover as much as possible, or wanted to give you introduction to as many topics as possible, so that, I mean, it's just an overview, right? And so that you could have your own interests and delve deeper into those topics. So this is what I wanted to do. So if you have any questions, you could ask me or mail them to me, or you could mail them to Dr. Ansuya and she could pass them on to me. So yeah. So I think this concludes today's talk.
Any questions? Uh, does anybody have any particular questions about this topic? It was very clear.
Yeah, I mean, if you don't have questions now, you could always mail me to mail those questions to me, so I can answer them. Or if you
Maybe I can ask one question. So you're talking about chips, and you talked, and we also saw certain coupling equations, electromagnetic coupling.
yeah.
So do you also find that as we shrink the sizes of chips, from what I've heard, that even pure magnetic coupling also becomes an issue because the conductors, which were supposed to be electrically isolated, they come so close to each other. And I mean, is that an issue at all in your modeling?
Yeah, that absolutely happens, right? Because now you have 2 points on the chip that you thought are isolated. That is, they don't have any coupling between them. As you shrink, the currents and the voltages, currents in one of the pins or one of the wires, the fields around it would induce voltages in the pins that is in the vicinity of it. So those are compatibility issues that are happen. So in, let's say, in a digital circuit, it could cause the 1 to become 0 or 0 to become 1 or 5 volts to become 2.5 volts, in which case the 2.5, the it's if it's 2.5 is logic 0, then you have a different logic that's being propagated. So those compatibility issues are supposed to be taken care of. Yeah.
And very interesting, you said that this can be used to actually detect I don't know, landmines or oil underneath. And
Yeah.
as you said,
So,
there
so
is
this is
so
yeah. So what if you take a method to a company like Shell or a British Petroleum or something, they would, if you have a method that says, you know what, I could send an electromagnetic signal and it goes to different layers of the earth. And finally, when it detects the permeability and permittivity that corresponds to the oil and it sends a signal to you, they will give you $1 million and buy that method. So these methods are that precious because let's say oil has a certain permeability and and the layers above it will have permeability which is close to the oil or slightly different from the oil. So your method should exactly be able to distinguish between the multiple layers in the media, right? For example, I gave the example of a transmission line which is broken in between. So there's a simple clear-cut break. So you have 50 ohms transmission line, and then suddenly there is a break. That is open circuit. That is a million ohms. There's such a huge change, and it's easier to detect that as compared to detecting oil under the earth, wherein the permeability doesn't change so abruptly. It changes in small, it changes very gradually. So for the reflection method to detect those small changes, it's much difficult. So that's why your modeling method should be that accurate. At every level, it should be able to discretize accordingly. Yeah.
Yeah, that is very true, because I was thinking you're going through ground, and usually
Yeah.
we consider ground to be like a perfect conductor.
Correct.
So
That's for 50 hertz. For high frequencies, you have the your media will have different permeability and different permittivities for
right.
every frequency, right? Yeah. They'll polarize and so on. So many factors will you have to take into account. So there's a frequency dependence also. That is, the if you send a Gaussian wave, the frequency at one frequency, the permeability at one frequency won't be the same as permeability at another frequency. You have to take that into account also. If you're doing a time domain solution, you have to do a convolution in that case, omega mu star into something, right? So there's a frequency dependence also, and anisotropy and so many things. That is, the wave propagates in a different way in
Yes,
different directions.
anisotropy is a huge issue over here. Okay, so anybody else would like to ask any questions? Otherwise, we'll wrap up the session. Dr. Rajat, would you like to give the vote of thanks? Yeah, I think we can wrap up the session then.
Yeah.
Dr. Rajat?
Hello, ma'am. Am I audible, ma'am?
Yes, you're audible.
Yes, ma'am. So thank you so much, ma'am, for like to mention speaker Dr. for his wonderful computation electromagnetics. Extend my gratitude for him. Take out time from page the event. Thank you, sir, for letting us.
Sure, no problem at all. Yeah.
Letting us the deep insights of.
Actually, your voice is broken, so I'm just guessing what you're saying.
Yeah, I think Rajat, Dr. Rajat, I think your voice is coming broken. Yeah, thanks a lot. And on a lighter note, I still see that, like UK sir used to always say, never put a variable in a single, like I saw a lot of ZZs.
Yeah.
Is
So
that
that's what,
something you still
yeah.
follow from him?
Yeah. That convention has always stuck to me. He always said that never use a variable in, just don't use T, use KT. Don't use
Ah,
just N,
yeah,
use
I
NS.
was noticing that.
Yeah. So that's, or like KZ, like for space, don't use just Z, use KZ. So I try to stick to that convention as much as possible. And I'm not able to leave that habit because, yeah.
But what was the logic behind that? Why? Why did he say that? I've forgotten.
I never asked it. I don't remember why he said that, but this thing always stuck to me because, but when I do in C++,
Yeah.
I usually just use one variable. But
Ah,
when I do MATLAB and when I do electromagnetic simulation, I also see here NT. I don't use
yeah,
just T
yeah.
or S. So
Exactly.
yeah, so this just stuck to me always for PP. Yeah, so LL, PP, CC. So this just capacity. It could be just C, right, for capacitance, but I
Correct.
use.
Exactly.
So this is just something that my professor taught me. So
Yeah, we all learned under him, and he's a brilliant professor.
yeah,
So,
so
okay, thank you so much, Santosh,
sure,
for taking the
sure,
time out, and
sure,
hope
no
to
problem.
keep interacting with you and working with you further.
Sure,
So,
thank you so much. Have a great day ahead. Yeah, bye.
thank you so much, everyone, for coming as well.